Section 1 Introduction. Let's dive into the fascinating world of language models. Just like teaching a person to read and write opens up a world of knowledge, scaling up language models, by increasing the number of parameters and the size of the training datasets, unlocks new and exciting behaviors. This phenomenon is often referred to as emergence. Early model designers noticed some of these emergent properties, and these observations have been confirmed through experiments with larger models like GPT, PaLM, and PaLM 2. However, emergence is not a single phenomenon, but rather a collection of phenomena. Trying to explain it solely through mathematical analysis of gradient-based training is quite challenging, and there's a growing belief that we might need new scientific theories to fully understand it. One question that often comes up in discussions about AI safety and alignment is whether a machine can exhibit new behaviors that it didn't encounter in the training data. If all learned behaviors were already present in the massive training corpus, then the AI safety issue becomes less pressing. This paper aims to provide a better mathematical understanding of these phenomena. However, there are some challenges. First, we don't have a clear mathematical definition for the set of language tasks of interest, nor a comprehensive list of the skills and abilities that the theory should cover. Linguistics research offers some useful mathematical formalizations, but integrating these into a single framework and connecting it to statistical learning, which underlies the cross-entropy loss used in language models, is a challenge. Second, we need to explain why multiple skills tend to emerge together. What's the connection between them? Lastly, we need a theory that explains how the ability to solve tasks that combine natural skills emerges from the theory. For instance, popular chat agents can give reasonable responses to questions that test their ability to combine skills. However, the number of skill combinations seems too numerous for all of them to have been seen in the training data. This paper introduces new types of mathematically rigorous analyses that stay close to statistical learning frameworks and offer plausible explanations for some of these phenomena. The theory imagines a two-sided graph with skills on one side and text pieces on the other. Text pieces are generated by an unknown process that takes random combinations of skills and converts them into a text piece that requires those skills. A key assumption is that prediction loss on the closed prompts captures the average cross-entropy loss of the model. Thus, understanding is connected to prediction in a statistical task. Even though the framework feels general and unspecified, the fact that text pieces are produced using random combinations of skills is powerful enough to imply that reduction in cross-entropy manifests itself as improvement in competence on the basic skills and combinations of basic skills. The rate of emergence is tightly governed by random graph theory, which we've adapted to allow arbitrary measures on text and skills. Section summary. As language models become larger and more powerful, they exhibit emergent behaviors that are not fully understood. This paper aims to better understand this phenomenon by exploring mathematical frameworks that connect skills and text pieces. By analyzing a bipartite graph with skills and text pieces, the authors propose that the reduction in cross-entropy loss leads to improved competence in both basic skills and combinations of skills. The rate of emergence is governed by random graph theory. Section: Potential conceptual frameworks for next-generation AI models. We're currently witnessing a transformation in the field of AI, where traditional language models are being reimagined as AI agents. This shift is moving away from the old approach of training a model to predict the next word in a text. Instead, we're now focusing on a more diverse and carefully curated mix of data, which could include code, mathematical reasoning, images, and more. This new approach could also involve different types of training losses. Our proposed conceptual framework is flexible enough to adapt to these changes, as it doesn't make any assumptions about what constitutes skills and text and how they interact. This framework can also accommodate prediction losses other than cross-entropy. For the sake of simplicity, we'll discuss this framework in the context of basic language modeling. The structure of this paper is as follows. The first section provides a brief overview of scaling laws, emergence, and random bipartite graphs. The second section explores the relationship between the reduction in excess cross-entropy and learning. The third section presents a key insight about scaling laws, suggesting that they provide a strong inductive bias for the development of complex skills. The fourth section introduces our conceptual and statistical framework for measuring skills through next word prediction. The fifth and sixth sections present concrete results about the emergence of skills as a result of scaling. The final section presents a brief experiment highlighting the predicted phenomenon of ease of learning skill combinations that have not been seen in the training data. Language modeling is based on a statistical approach. It assumes that occurrences of linguistic units, like words, sentences, paragraphs, follow a statistical pattern. Therefore, pieces of text from a large and diverse corpus are considered to be samples from a probability distribution. Language models are trained to predict the next word in a text, given a certain number of preceding words. For example, given the past 500 words, the model's task is to predict the next word. Humans, when faced with this task, could provide many possible completions, and the model assumes that the frequency of these completions can be represented probabilistically. So, the model calculates a probability for all possible next words. The effectiveness of a model is determined by its cross-entropy loss, which is calculated for a sequence of words. Models are trained by minimizing this training loss on a text corpus, and their effectiveness is determined by their test loss, evaluating the same loss expression on a separate text from the same corpus. Often, the training corpus is so large that the model trains only once, or a few times, on each piece of text, and by the end, the test loss on separate text is almost the same as the training loss. Section Summary. The shift in AI models involves moving away from training models solely on predicting the next word in a text corpus and instead using a curated combination of data, including code, math, logical reasoning, and images. The proposed conceptual framework is adaptable to these new settings and can measure skills through next word prediction, with the analysis also applicable to different prediction losses. The paper also explores scaling laws, emergence, and random bipartite graphs, and presents results on the emergence of skills and the ease of learning unseen skill combinations. Section: Scaling laws. Let's delve into the concept of scaling laws. These are mathematical formulas that we've derived from empirical data. They explain how the performance of a model, measured by the test cross-entropy loss on unseen data, changes as we adjust the number of model parameters, n, and the size of the dataset, d. For a specific type of model, known as chinchilla models, we found the following relationship. The loss, L, is equal to a constant, A, plus 2 fractions. The first fraction has a constant, b, in the numerator and the number of model parameters raised to the power of minus 0.34 in the denominator. The second fraction has another constant, c, in the numerator and the size of the dataset raised to the power of minus 0.28 in the denominator. For this particular model, a is approximately 1.61, b is around 406.4, and c is roughly 410.7. This formula, which describes the overall behavior of the model, is reminiscent of the second law of thermodynamics. It allows us to bypass the need for a detailed understanding of the training process. Our theory only needs the general form of the equations, specifically, the inverse polynomial dependence on n and d. This makes it applicable to other training frameworks, such as overtrained models, where similar scaling laws have been observed. Next, let's talk about emergence. This term refers to an intriguing observation. As we increase the number of model parameters and the size of the dataset together, the model's performance on a wide variety of language tasks tends to improve in a correlated manner. This improvement can seem sudden when we plot the parameters on a logarithmic scale, but it's generally agreed that for most tasks, the performance improves gradually as we scale up the parameters. Hence, the term, slow emergence, is more accurate. It's important to note that the rate of emergence varies across tasks. It's usually faster for tasks that closely resemble the text found in the training data. There are many tasks that current models struggle with, and these tasks are often quite different from the typical text corpora. For a more detailed discussion on the emergence rates across various language tasks, refer to the Big Bench dataset. Based on these observations, one could reasonably argue that the emergence of skills comes from training on tasks that are similar to those that were implicitly solved during the next word prediction in the training dataset. This is indeed our starting point. Section Summary. Scaling laws describe how the test cross-entropy loss on held-out data scales with the number of model parameters and the size of the dataset. These laws can be used to understand the macro behavior of training without needing a detailed understanding of the training process. Emergence refers to the phenomenon where increasing the number of model parameters and dataset size improves the model's performance on a range of language tasks, with the improvement occurring gradually rather than abruptly. This suggests that training on similar tasks implicitly solves other tasks, such as next word prediction, in the training dataset. Section: Poverty of stimulus with respect to skill combinations. Let's delve into the issue of skill combinations in relation to artificial intelligence. When interacting with popular chatbots, experts often notice that these AI systems seem to be able to handle tasks that require a mix of basic skills. However, the sheer number of possible combinations of these skills, for instance, if we consider 4 skills at a time from a pool of tens of thousands, seems too vast for all of them to be represented in the training data. This brings us to the concept of the poverty of stimulus. The term, poverty of stimulus, was coined by Chomsky to describe the idea that children don't have enough data to learn language, suggesting that evolution must have equipped humans with a built-in, universal grammar. Similarly, our language model, which starts learning from random noise, seems to overcome the lack of stimulus in terms of skill combinations. This surprising phenomenon is driven by the scaling laws, a topic we'll revisit later. Now, let's consider a common confusion among researchers regarding the emergence and scaling laws. They often wonder why a small decrease in loss when we increase d from 10 to the power of 11 to 10 to the power of 12, which results in a tiny change in cross-entropy, can lead to significant changes in macroscopic behavior. To understand this, we need to consider the inherent cross-entropy in language, which arises from the many possible correct choices for the next word in a text. This inherent cross-entropy is represented by the term A. No matter how good a model is, it can't achieve a lower cross-entropy than A. We argue that the rate at which the model makes errors, due to its misunderstandings of the text, is linked to the excess cross-entropy over this minimum amount. This excess is represented by the second and third terms of the equation. Interestingly, this excess does decrease noticeably with scaling. For example, when n and d are increased by a factor of 10, it reduces by roughly 2, which is 10 to the power of 0.28. Section summary. Popular chat agents are able to solve tasks that require combinations of simple skills, but the number of possible combinations is too large to be present in the training dataset. This poses a poverty of the stimulus issue, similar to the problem of babies not having enough data to learn language. However, the language model in this study defies this issue due to scaling laws. Additionally, the decrease in loss when increasing the dataset size does not directly correspond to a decrease in macroscopic behavior, as there is an inherent cross-entropy in language that cannot be surpassed. The rate at which the model makes mistakes is connected to the excess cross-entropy over this minimum amount. Section. Excess cross-entropy drives learning. In this section, we're going to introduce a crucial concept in our theory. The reduction of excess cross-entropy is what fuels progress in language tasks. Let's illustrate this with a well-known example that inspired the Winograd Schema Challenge, WSC. The city councilman refused the demonstrators a permit because they feared violence. In this sentence, the pronoun, they, is ambiguous. It could refer to either the demonstrators or the city councilman. Winograd noted that to clarify this ambiguity, i.e., to resolve the anaphora, we need knowledge about the world that isn't provided in the text itself. Specifically, we need to know that demonstrations can become violent and that city councilmen generally want to avoid violence. The WSC includes many such examples from a variety of contexts, which tests the model's understanding of the world and common sense. A key strategy in creating tests for language comprehension, like the WSC, is the close procedure. This method is also commonly used to assess language development in children. To evaluate the model's understanding of the pronoun, they, in our example sentence, we can add a question: who feared violence? This question can be followed by a blank space or multiple choice answers, as city councilman. B. Demonstrators. For WSC examples, a human would be completely certain of the answer. However, language models around 2016 were about evenly split between the two options. In our example, a human is completely sure of the answer, which means their cross-entropy here is the logarithm of 1, or 0. But if the model is evenly divided between the two options, this means it has a cross-entropy of the logarithm of 2, which is all excess cross-entropy. Considering how often pronouns are ambiguous in English, we can conclude that a model that hasn't learned to disambiguate pronouns will show a lot of excess cross-entropy in many parts of the text. Therefore, reducing excess cross-entropy will likely eliminate such errors. It's important to note that typical text corpora don't usually contain these artificial close questions. However, it's plausible that the model's fundamental misunderstanding of the type we've discussed could frequently lead to prediction errors in nearby text. We'll delve into this in more detail in a later section. Section summary. The key idea presented in this section is that reducing excess cross-entropy improves performance on language tasks. An example is given using the Winograd Schema Challenge, which tests a model's understanding of ambiguous pronouns. The theory suggests that models with high excess cross-entropy are more likely to make prediction mistakes in neighboring text, highlighting the importance of reducing this measure. Section 4. Scaling law implies slingshot generalization. In this section, we're going to explore the concept of the scaling law and how it implies a powerful learning capability, which we'll refer to as the slingshot generalization. This is a preliminary discussion to set the stage for our main theory. Let's start with a simple thought experiment. Imagine that there are basic language skills, and each piece of text uses exactly one of these skills. If we divide our training and test datasets into S equal parts, each representing a sublanguage, then the size of each sublanguage would be the total dataset size, D, divided by S. Our previous work suggests that the rate of learning can be roughly measured by the excess cross-entropy. So, if we apply all S skills to test tasks, the average error would be the per-word excess cross-entropy of the model trained on the full language. According to the scaling law, this scales as 1 divided by D raised to the power of 0.28. However, if we were to train the model using data from just one skill, the scaling would be S raised to the power of 0.28 divided by D raised to the power of 0.28. This is worse by a factor of S raised to the power of 0.28, assuming the model size is the same in all cases. Since S is likely to be large, training on the full dataset gives much better performance on individual skills than if we trained separate models on individual skills. We refer to this effect as slingshot generalization. This phenomenon is similar to the concept of effective data transfer, which is used to measure the effectiveness of pre-training. If we use a small labeled dataset for supervised training of a classifier by fine-tuning a pre-trained language model, we usually get better accuracy than training the classifier using only the labeled dataset. This improvement can be seen as an effective transfer of knowledge from the model's pre-training. From a learning theory perspective, if the model is trained on a single skill, its error on tasks related to that skill should be at least the reciprocal of the square root of the dataset size, which is 1 divided by the square root of ds. However, when the model is trained on all S sublanguages, the scaling law makes the error on the average skill decrease as 1 divided by D raised to the power of 0.28. At first glance, this might seem to contradict learning theory. But learning theory allows for the inductive bias of the model. The error estimate for training on a single sublanguage assumes no inductive bias. The correct interpretation is that training using all S datasets provides a strong inductive bias for learning on each individual dataset. This inductive bias likely comes from the model's architecture and its ability to gather structural information from all S sublanguages, which improves learning on individual languages. This is something we intuitively understand. Learning your sixth language is easier than learning your second. Section summary. The scaling law implies a strong inductive bias in learning, which leads to high learning capability. By training a model on a full language dataset that consists of multiple sublanguages, the average error on test tasks involving any of the sublanguages decreases as the dataset size decreases, following a scaling law of 1d(0.28). This effect, known as slingshot generalization, allows the model to perform significantly better on individual skills compared to training separate models on each skill. This phenomenon is related to effective data transfer, where pre-training a model improves its performance on downstream tasks by transferring knowledge from the pre-training phase. Section 5. Statistical formalization of skills. In this section, we're going to delve into the mathematical framework that helps us understand skills and their relationship to language comprehension. We're going to bypass the complexities of training and generalization, focusing instead on how the model behaves when tested. We're assuming that the test data is a long string of text pieces, and we're evaluating the model's understanding of this data through a prediction loss. Let's start by defining a few terms. Our test data is a large collection of text pieces, each made up of a certain number of tokens. Each text piece has a prediction loss associated with it. We also have a set of underlying skills that language possesses. We visualize this as a bipartite graph, where one set of nodes represents skills and the other represents text pieces. An edge connects a skill to a text piece if that skill is needed to understand the text piece. However, this is a very general framework and we don't have a complete understanding of all the skills or how they connect to the text pieces. So, we make a few assumptions. First, we assume that we can test the model's understanding of a text piece using closed prompts, which are commonly used to evaluate language development in children. We also assume that each text piece requires a specific number of skills, and that these skills are chosen randomly from a distribution. Finally, we assume that there's a process that can convert a randomly chosen set of skills into a text piece that requires those skills. We then define a skill cluster as a collection of text pieces that are generated by choosing a subset of skills and using them to create a text piece. We also add closed prompts to the text piece to test the model's understanding. The prediction loss on the text piece is calculated by predicting the answers to the closed questions. We also make the assumption that the closed questions capture the model's prediction loss accurately. This allows us to associate a statistical task with each skill, where the task involves predicting the closed questions in a subset of text pieces that require that skill. For example, if a text piece requires 5 skills, it will appear in 5 statistical tasks corresponding to the individual skills, as well as tasks corresponding to pairs of skills, and so on. However, this method assumes that if the model answers a closed question incorrectly, the loss is incurred in all these statistical tasks. This doesn't take into account the possibility that the model may have only misapplied a subset of the skills. In practice, the model may be able to apply the skill more effectively on other distributions of text pieces than the one seen in training. However, this is not taken into account in our statistical view. Section Summary. In this section, the authors present a mathematical framework for understanding skills and their relationship to language comprehension. They define a test stream consisting of text pieces and a skill graph that connects skills to text pieces based on the prediction loss required to comprehend them. The authors make assumptions about the test stream, the mixing of skills and text pieces, and the generation of text pieces using random combinations of skills. They also introduce the concept of degree K skill clusters, which are collections of text pieces generated by nature based on a subset of K skills. Finally, they define statistical tasks associated with each skill cluster and skill, allowing for the interpretation of skills in the context of statistical learning theory. Section 6. Deriving Emergence, Uniform Cluster. In this section, we delve into the heart of the matter: how the reduction of a model's excess cross-entropy, due to scaling, enhances its performance on closed tasks inserted in the test stream. We also explore how this improvement affects performance on statistical tasks related to skills and combinations of skills. We start by examining a simple scenario where the test stream consists of a single cluster of skills of degree K. In this scenario, the skills and the text pieces are uniformly distributed. This means that the distributions mu_1 and mu_2 in the definition are uniform. We will later expand this analysis to more general settings. A common but incorrect approach to understanding this is to assume that each text piece is linked to a random K tuple of skills, denoted as vec S. One might be tempted to explain emergence through the linearity of expectations, specifically, a relation about prediction loss. However, this approach is flawed. To understand why, let's consider Y, a subset of text pieces where the model makes errors on closed questions. This subset Y is influenced by the skill graph and the unknown processes gen and close of the definition, which can introduce arbitrary correlations on text pieces. Since the model has been exposed to part of the test stream, the training data, it has gathered some information about the unknown skill cluster. Therefore, at the end of training, the locations of errors in the test stream, or the set Y, are arbitrary and dependent on the skill cluster. Our analysis can assume an upper limit on the test loss, but we can't predict where it will occur. This is the main mathematical challenge we face, and we will overcome it using random graph theory. Let's say the model makes a mistake on a text piece if the prediction loss on the included closed questions is at least 1/2. This is the kind of error that would occur if the incorrect answer is chosen with a noticeable probability on a single multiple choice question. Given that the average cross-entropy loss for the text pieces is delta, we can conclude that Y consists of at most 2 delta fraction of text pieces. Our next result assures us that statistical tasks related to most skills do not assign significant probability to text pieces in Y. In other words, the model performs well on statistical tasks associated with these skills. This theorem is a simple rephrasing of a lemma in the appendix. The theorem states that regardless of the details of the gen and close processes, a certain property holds with very high probability in a single skill cluster with uniform distribution of skills and text pieces. Let Y be an arbitrary subset of text pieces consisting of theta fraction of text pieces. If certain conditions are met, then at least one alpha fraction of skills have at most beta theta fraction of their edges connected to Y. As the model scales up, the set Y will shrink, meaning theta will decrease. Since edges between a skill node S and set Y correspond to errors in the statistical task T_S, the theorem provides an upper limit on the prediction error in statistical tasks corresponding to 1 alpha fraction of skills. We also present performance curves, which show the set of alpha, beta combinations satisfying the theorem for a given theta, K. For example, a point, 0.8, 0.16, on a curve means at least 0.8 fraction of skills have at most 0.16 fraction of their edges in the error set, Y. We observe that as we increase K, the emergence curves shift down noticeably, implying the emergence of more skills. A lemma shows that this trend always holds, and it follows from the fact that theta is a decreasing function in the interval 0, 1. The theorem shows that for a fixed prediction loss theta, using a higher K implies better emergence of skills. Since K represents the number of skills used in a text piece, it intuitively measures the complexity of the text. For example, a college text would be expected to have a higher K than a primary school text. As theta scales according to the scaling law, our theorem predicts that more complex text will be more effective at inducing skills, provided the scaling laws don't change. This prediction aligns with experts' intuition, although we are not aware of a study of scaling laws for text of different quality. Section Summary. In this section, the authors analyze the emergence of skills in a simple setting where the test stream consists of a single skill cluster. They point out the incorrect way to reason about emergence and introduce a mathematical hurdle that their proof will overcome using random graph theory. They also present a theorem that guarantees good performance on statistical tasks connected with most skills and show that as the model is scaled up, the set of errors in the test stream shrinks, indicating better emergence of skills. Section 6.1 Emergence for K-prime, tuples of skills. Let's delve into the concept of the emergence of K-prime tuples of skills. We're going to evaluate how well our model performs on statistical tasks that correspond to these tuples. To do this, we'll think of these tuples as composite skills, and then recalculate our model's performance. Our first approach is a simple one. We observe that a random K-tuple is a combination of K-prime random K-prime tuples. If we think of these tuples as composite skills, we can create a skill graph with a degree of K-prime. This allows us to derive performance curves for these tuples. However, this method is often weak and can lead to trivial estimates. Our second approach is more effective. We recombine the test stream in a K-prime-wise manner. We divide the test stream into subsets of size K-prime and then join the K-prime text pieces within each subset to create a larger piece of text, which we call a K-prime piece. We keep all the original questions for the old test pieces and don't add any new ones. If the model's error per average text piece was delta, then the error per average K-prime piece is K-prime times delta. Each K-prime piece now uses a random K-prime K-tuple of skills, which we can also view as K-random K-prime tuples. By viewing these tuples as composite skills, we can use them as the skill set in our theorem, which gives us a clear way to measure the performance on tasks corresponding to these tuples of skills. We can summarize this in lemma 7. If we consider a skill graph where S' consists of all K-prime tuples of skills, T' consists of K-prime pieces, and the E consists of S', T', where S' is a K-prime tuple of skills and T' is a K-prime piece where this tuple of skills is used, then for any alpha and beta greater than 0, with beta greater than 1 and alpha times beta less than 1, there are at least one alpha fraction of K-prime tuples of skills that have at most beta times theta fraction of their edges connected to Y. Interestingly, we can see generalization. If we assume a chinchilla-like scaling law where increasing the scale by 10 times leads to a 2 times reduction in excess cross-entropy, then if a model performs reasonably well on individual skills at its current scale, then after scaling up by 10 times, we would see similar performance on pairs of skills. If we scale up by another 10 times, we would see similar performance on 4 tuples of skills, and so on. These are provable lower bounds on performance gains, but the actual gains could be higher. Corollary 8 states that when we scale up a model M1 with loss delta so that the new model M2 has loss delta, K', then the performance curve for K' tuples of skills using M2 is identical to the curve for individual skills on model M1. This leads us to a situation of paucity of stimulus. Suppose we trained a language model with D tokens. After scaling by K orders of magnitude, i.e., increasing dataset size to C to the power of K' times D tokens, where in the chinchilla framework C is around 10, the performance on K' tuples of skills is as good as what the performance was on individual skills before the scaling. However, the number of K' tuples of skills is around the size of the set of skills to the power of K'. This quickly leads to a shortage of stimulus for some fixed K'. For example, if we trained a larger model on 10 trillion tokens, it should display proficiency in most 8 tuples of skills, despite not having seen most of those combinations in training. Section Summary. In this section, the authors discuss the emergence of composite skills and their impact on model performance. They propose 2 estimates. The first estimate considers random K tuples as a union of K, random K, tuples, while the second estimate involves a K-wise recombination operation on the test stream. The authors also present a corollary that suggests if a model performs well on individual skills, it will likely perform similarly well on skill pairs, 4 tuples, and so on, after further upscaling. Additionally, they highlight the paucity of stimulus situation, where the number of K tuples of skills exceeds the available training data, leading to a lack of exposure to certain combinations of skills. Section 7 Emergence Analysis with General Measure on Text and Skills. In this section, we're going to delve into a more complex analysis of the relationship between text pieces and skills. We're going to use a general measure, which we'll denote as mu_2, t, for text pieces and mu_1, s, for skills. Our previous statements, such as the lemma and those in other sections, still hold true in this context. The only difference is that we're now dealing with measures instead of simple counts. We'll start with Theorem 9, which discusses the emergence of skills and combinations of skills. Let's imagine we have a subset of text pieces, y, which has a total measure of theta. Each text piece in this subset has a measure that is significantly smaller than theta. We'll also define two positive numbers, alpha and beta, where beta is greater than 1 and the product of alpha and beta is less than 1. The theorem states that if a certain inequality holds, specifically, if the sum of the entropy of theta and a function of alpha, beta, and theta is less than 0, then the measure of skills that have at most a fraction of beta times theta of their edges connected to y is at least 1 minus alpha. This also applies to combinations of skills, with the same modification from count to measure. To prove this, we first consider the measure mu_1 on skills. This is straightforward to handle by replacing each skill with a number of copies proportional to its measure, mu_1, s. This effectively changes the measure to a uniform one. However, the measure mu_2 on texts is trickier to handle. If we try to replace mu_2 with a uniform measure by duplicating the text pieces, the connections between the text pieces and the skills become correlated, not random. To overcome this, we need a more nuanced argument. We start by randomly selecting a subset of text pieces, y, whose size is proportional to theta times the total number of text pieces, and a subset of skills, z, whose size is proportional to alpha times the total number of skills. We then calculate an upper bound based on the expectation that z has more than a certain fraction of its edges connected to y in the presence of the measure mu_2. We choose y by independently selecting text pieces with a probability proportional to theta times mu_2, t. We still choose z randomly as before. We then apply Jensen's inequality to the same calculation, which gives us the same upper bound as before. For more details, you can refer to the lemma in the appendix. Section Summary. In this section, the authors analyze the general setting of a definition where text pieces and skills have measures. They state that their lemma statements hold with cardinalities replaced by measures. They then present Theorem 9, which states that if certain conditions are satisfied, the measure of skills that have a fraction of their edges connected to a subset of text pieces is at least a certain value. The authors provide a proof that involves reasoning about the measures of skills and text pieces, and they use a subtle argument to handle the measure of text pieces. Section 7.1 Extending Theory to Multiple Clusters. In the previous sections, we've been working under the assumption that there's only one skill cluster in a language. However, in reality, a language can have multiple skill clusters. For instance, a standard language corpus might contain a large skill cluster of everyday text and the basic language skills and world knowledge needed to understand them. There could also be smaller clusters related to specialized topics like finance, science, or mathematical reasoning. We're assuming that each text piece belongs to only one cluster, but the skills could be part of multiple clusters. If each text piece is part of just one cluster, then our previous analysis still holds. The total loss is the weighted sum of the measure of text in each cluster. So, reducing the overall loss will drive the emergence within individual clusters. However, our theory doesn't provide any mechanistic insight, so we can't predict the rate at which the loss decreases, and hence emergence, within clusters. This relates to an earlier point in the paper about the lack of detailed study of scaling laws for different types of corpora, as well as for training on mixes of corpora. We'll leave a more detailed analysis, possibly allowing for a hierarchical structure in clusters, for future work. As always, simpler settings are likely to provide the main insights. Now, let's move on to a simple experiment that illustrates our theory. We've noticed a surprising phenomenon. The inductive bias of pre-training implies that combinations of skills emerge as naturally as individual skills. To illustrate this, we conducted an experiment involving vision tasks on pre-trained VIT models. We created a dataset of 1,000 composite images. Each image was made by randomly selecting 4 images from the MNIST dataset of handwritten digit images and placing each in one quadrant of the composite image. We assigned a fixed label to the composite image, which was the label of one of the 4 digits, chosen at random. This was the target label, while the other 3 digits were considered background labels and were not made available during training. We trained a linear probe on top of the input embeddings of the composite images output by a pre-trained vision transformer, VIT-clip, model. The model was pre-trained on a custom image dataset and we used mini-batch SGD for training. We tested the model using held-out images, which were composites made from MNIST images that hadn't been used to create the training set. This ensured that the model encountered new composite images during evaluation. The final classifier, being softmax, can output the top 4 labels just as easily as the TOP1. Doing so achieved approximately 92% accuracy in classifying the 4-digit tuples, even though it was trained using only 1,000 examples labeled with a single digit. Full fine-tuning of the model yielded around 95% accuracy with 1,000 labeled examples. To understand why this happened, consider that since the provided label is fixed by randomly picking one of the 4 digits in the image, the optimal softmax output should learn to give equal logit values to labels of all 4 digits present in the image. The figure describes the skill cluster implicit here.